Thank you very much, Speaker, and I appreciate the organizers for allowing me to speak today. I was supposed to speak on Monday, but because of a storm in Europe, I had to cancel my flight. So I'm grateful for the flexibility shown here by the organization. As was just mentioned, I'd like to talk about refurbishing old equipment using new technologies that are available today. So I think it's a matter of time before equipment starts to malfunction or it just gets old and needs to be replaced or something like that. We all know this. So instead of replacing the equipment, sometimes it's worthwhile to take a look at actually retrofitting it to actually increase the performance of the vessel, sometimes making it better than it was even originally intended to be. So first I'll take you through some principles of retrofitting. These are the same principles that are used for revamps in general, but they can also be used for replacing individual pieces of equipment. So as you can see up here, in general, whatever we would like to do, we want to make sure that we use all the existing margins in the equipment that's available. Now, typically, when the equipment was designed originally, there were some margins put in there for various reasons. So when the plant is running, we want to make sure that we use all of those available margins as much as we can. So what we do is we tend to go into the plant. We take detailed measurements about the plant, how it's running. We talk to the operators there in the plant. And then we take all this information and we go back home. We do our homework there. And we evaluate the running plant and that piece of equipment that's to be exchanged. And this is typically done by a process engineer together with equipment engineers. And then the next phase, what we do nowadays, since the past few years, the strong computers have made this possible. We do CFD modeling to do, let's say, theoretical design of the new internals or the new vessel that's to be installed. So this is important because it allows us to, let's say, play with things and get an optimal design before we actually go to the workshop and put this thing together. And this wasn't possible up until recently because of the computer speeds. So this design is typically done, it's more of an iterative approach. And this involves typically a whole team of engineers. Usually the process engineer is leading the way, but also the mechanical engineers and CFD modelers and estimators and all these kinds of people are involved. So then after this is all carried out, and they have a theoretical design on the computer, which is an optimum way that this vessel should be working once it's filled. This thing has a mind of its own, I have a feeling. Which button is for? Okay, so the important thing to note is when there are some things to be done in the plant, whether it's replacement of a vessel or just changing out the internals to improve the performance, there's usually a tendency to go for the cheapest option, which is typically a one-to-one replacement. So you just replace it exactly as it used to be. The problem with this is, even though it is, let's say, tempting to do to save money up front, you lose the opportunity to make improvements to your plant. And these improvements that you can make, they typically require a little bit more investment. These investments, they typically pay for themselves in just a matter of a few years, depending on what's to be done. So we highly recommend that if there is some work to be done in the plant, you investigate the ability to, or the possibility to upgrade this piece of equipment, even if it's only just about the internals of equipment. As I said, this can really pay dividends in the future. So I'd like to take you through two case studies that we actually did. One is involving a retrofit of secondary reformer. It was actually a retrofit done actually here in Egypt a while back. The second one will be involving ammonia converters. We have a new kind of cartridge for our ammonia converters, and I'd like to take you through the design. So the situation is as follows. The client operates an ammonia plant. It's a few decades old, actually. And even back then, the plant was not actually sold as, let's say, state-of-the-art kind of plant. It was sold essentially just to be a cost-effective way to produce ammonia. This plant has been undergoing, let's say, minor upgrades throughout the years already. And a few years back, they started to have some problems with the methane slip coming from the secondary reformer. So they asked us for help, and originally their plan was to completely exchange the secondary reformer for a new secondary reformer with a new modern technology that you'll see here in a few minutes. So the CH4 slip was steadily rising. I think they were up above 0.6% at this time. And they really wanted to get back down to around the area of 0.2%. So we convinced them of instead of completely replacing the existing vessel, which would have cost, let's say, somewhere around 4 or 5 million US dollars, with considerable outage also in time for the replacement. We decided to look at a retrofit of the internals of the secondary reformer to make it perform in such a way that resembles new technology that we have today. So this is a general arrangement diagram of the existing secondary reformer. So this is an old Uhde reformer, like I said, almost 30 years old, I think. So it has the typical signs of the reformers back then. We have the inlet coming from the bottom, right, from the reformer, and going up into the center tube is the syngas, and then the syngas comes out of this distributor into the combustion zone. Here we have one single nozzle for the air intake, and this air is directed into the inside of the secondary reformer through that one nozzle to the ring burner. So this is how it used to be back then with the ring burners. So there you have in the combustion zone the syngas reacting with the oxygen in the air, and then after that going through the catalyst bed. So most of the reaction happens up in that convection zone, and the last little bit of reaction happens in the catalyst bed. So and then ultimately you have the outlets to the gas cooler. So as I said, this area up on top is actually very, very critical. So if you don't have good, proper mixing here, you won't have a very effective reaction. So the reaction actually takes place in two steps, right? So most of it happens up in this convection area. This is where the burning actually happens. And then the second part of the reaction happens down below in the catalyst bed. So this is more like, let's say, just removing those last little bits of methane. So it's extremely important to get uniform flow up in the combustion zone, of course, because the proper mixing means proper combustion, and also the velocity of the gas going through the catalyst bed is very important as well. It has to be a nice, even flow. So once again, here's the existing design. This is blow up of just the combustion zone. And there you can see the two differences, the old design to the new design. The old design has the internal ring burner, so this is the metal pieces that are exposed to the high temperatures. And if you compare this to the new design, I think you can see the advantage. The new design has the burners. They're actually not even burners. They're just jets that are on the outside. They're protruding through the refractory, so you have no metal pieces that are touching the flames in the hot temperatures. And in fact, if you look in from the top, a view from the top, as seen like in this diagram, the jets they're not protruding into the refractory just straight away. They're sort of tangentially arranged, so that you get a nice swirling motion, as shown in this CFD diagram. Once again, this is a diagram showing a CFD from a new modern secondary reformer. So you get a nice swirling pattern which gets a nice mixing motion up in the convection zone. And you can see on the left side, this is a CFD showing the nice distribution of temperatures, very, very uniform, going all the way down into the catalyst bed. And this is exactly what you want. So the objective is then to transfer this new technology somehow using the old vessel, right? And in this case, CFD modeling is also very, very important. So we can do trial and errors digitally instead of with an analog, with real equipment. So this is the first attempt that we had to model the existing secondary reformer. Okay, so this is a CFD model of the existing reformer. You can see this is only showing, first of all, the syngas coming out of the distributor. So the model was done. There's actually two streams combining here, but you can separate these two out just for the sake of understanding what's going on. So this is showing only the path of the gas coming out of the distributor up on top. And if you compare that, this is the one on the left only showing the pattern of gas coming out from the ring burner. This is the air. And I think it's very apparent that the mixing here is going to be very poor. So you can see on the left the air is basically just coming out of the ring burner and just shooting straight down more or less towards the catalyst bed. Back then we didn't really care too much about efficiency, so when these were designed, they were just these nozzles on the ring burner were just sort of put on there without giving too much thought to it. But you can see what happens as a result. You can see on the right side these eddy currents happening, these vertical eddy currents. This is an indication that the mixing is actually quite poor, and this is definitely what we do not want. So the next slide shows CFD pictures of the distribution of temperature. I think it's easy to see here too that the temperature distribution of the old equipment was very poor. On the one side you had very hot gas, on the other side it was cold still. Looking down towards the catalyst beds, you can see that these temperature distributions are also very poor. So in the areas where the temperature is actually very hot, in these areas actually the reaction is already completed. So the gas continues down through the catalyst bed, but the reaction is already completed anyway. So there's nothing really happening in that area in the catalyst bed. And on the other side you have, on the other side in the cold areas you have the combustion is not completed. And this also goes through the catalyst bed, but the effectiveness of the catalyst bed at that area is not enough because it's just not in the catalyst bed long enough to convert all of that gas, right? So it's a very ineffective way of operation. So for the new design, we focused, as I said before, on computer modeling. This is what a computer model tends to look like. What this does is it gives us ways to try all different sorts of geometries of the new equipment inside the existing equipment to find an optimum. And these interactions are extremely important and very, very sensitive, so it has to be done just the right way. The nice thing about this, though, as I said before, it allows us to experiment with different configurations without having to actually build the equipment to see how it works. So this is a diagram that we just saw. This is the air coming from the ring burner of the existing secondary reformer. And as I said, you can see that the mixing is very poor. It's just going pretty much straight down into the catalyst bed. If you compare this to the new design, I think it's actually very obvious to see which one has a better mixing. This one on the right is exactly what you would like to see in your secondary reformer. And in fact, this is modeling that is approaching what we would expect in a new secondary reformer via this configuration that we've seen before. So here's a picture we saw before too. This is the synthesis gas side. Here we saw these vertical eddies happening with the poor mixing as I described earlier. And if you compare that to the new design, you can see also very obviously that the mixing is much, much better. And once again, this mixing is done by let's say approaching how a new reformer, a new secondary reformer would operate with this swirling motion. So here's this is a comparison of the CFD modeling. The one on the left we just saw. This is the velocity and actually also the temperature distribution right above the catalyst bed. And the right picture is showing the new design. And here I think it's also very obvious to see which catalyst bed would be more effective, right? So, and this is actually a crucial step. So the last little bits of conversion are being done here in the catalyst bed. So it's extremely important that the mixing is done and as much of the reaction has already taken place before the gas gets even into the catalyst bed. So for the results in general, we had much less CH4 slip. The original design for this vessel 20 or 30 years ago was 0.3% CH4 slip. They were running upwards around 0.6%, sometimes even higher. And after this configuration, we actually got down to below 0.2. This saves money. The more the natural gas costs, the more money is saved. And the most important thing too is this is one success story where we were able to retrofit for very low cost, which was only about 10% of the cost of the new vessel. So here are some pictures of the fabrication of the vessel. So I mean, these look like just ordinary pipes, but these bends and the diameters and exactly the exact placement and the angles and this is all very, very important. So we had this all on the CFD model. So then it was up to us to make sure that it was actually built the way the CFD model said we should have built it. So yeah, as it turns out, it was built in the right way, and this was a nice success story for us. So the next case study is regarding ammonia converters. So the ammonia converter, as we all know, is also just a matter of time before it has to be exchanged. Typical lifetime of a cartridge is about 20 years. Some go as much as 30 years, but between that 20 and 30 year time frame, we usually hear about a lot of damages that occur and the catalyst breaking through and that sort of thing. So we recommend actually every 20 years changing out the cartridge. And as I said before, in this case, a one-to-one exchange is probably the cheapest way to go, because you can just take the designs from the original vessel or cartridge and just go to the same workshop and tell them to build it again. This can for sure be done, but as I said before, this makes you miss out on an opportunity to improve the performance of the plant. And actually the ammonia converter is the heart of the ammonia plant, of course. So it's extremely important that you get the most efficient internals that you can get for this. And especially for this piece of equipment, we've done a lot of work with entirely new designs, which I'll show you in a minute, but also for the existing design that you might know, optimizing, let's say, the standard cartridge to be able to get 20 to 30% more catalyst inside of the existing vessel. So this is, of course, very important for more production, or if your goal is these days to save energy, then you can, let's say, produce the same amount of ammonia, but produce that ammonia in a much more efficient way, saving natural gas. So the one I would like to show you, though, the option is involving a new kind of cartridge that we've been working on. I like to keep it a little bit simple and only show two-bed converter. I think most converters here in Egypt are three-bed converters, but the two-bed converters we typically have in our very large plants, which is a little bit of a paradox, but the largest plants, they have two-bed converters simply because they tend to have two or even three ammonia converters in total. So I want to focus then on this with the upper portion of the converter where the heat exchanger is. So I think this is the same configuration as most of the Egyptian plants as well, where you have the shell and tube heat exchanger. You can see on the right-hand side sort of a schematic representation of the same thing that you see on the left. So you have the gas coming in. It's still too cold to react. So we pass it through the tubes of the heat exchanger and warm it up to a nice 390 degrees Celsius, so it's at the reaction temperature. And then we pass it through the first bed of the converter, and there it's heated up to, it reacts and it's heated up to 520 degrees roughly as a result of the reaction. And then of course we want to get back down away from the equilibrium curve, so we cool it down against the gas that's coming in. And then this cooled gas goes directly onto the next bed where it passes through that bed as well, and so on. So this design I'm about to show you is actually something we've been focusing on more for new plants because it's very competitive these days, and we're trying to find ways to reduce the cost of new ammonia plants. And this vessel is actually very expensive because it's a large vessel. It has very thick walls because of the high pressures involved. But it can also be used for revamps as well. And for a revamp, typically you have the vessel. There's no reason to exchange the vessel, so you have a fixed size where you remove the old cartridge and you can install a new one. And other than that fixed size, you can do new things as you wish inside the vessel. So our goal was to try to reduce the pressure drop as much as we could because today, as I said, everybody's trying to save energy or produce more ammonia. And with this new design, you can do either or a combination of both somewhere in between. So this should be a familiar picture to you. This is just a shell and tube heat exchanger. I think every one of you has this, a few of these in your plants. So typical shell and tube heat exchanger. You have two inlets ports, two outlet ports. Very simple shell and tube heat exchangers. They're of course known for having a huge surface area, but they're usually used for low pressure applications because of leakages, that sort of thing. But we decided to try to use plate heat exchangers for high pressure applications, including in ammonia synthesis reaction. And the way we did that was to take the plate heat exchanger and modify the flow pattern in such a way that we're actually coming from the sides through, as you can see in the animation there. We're coming through the sides out the catalyst bed and going directly into the plate heat exchanger. And you can see that these in this round diagram here, basically the catalyst bed is circulate all around this plate heat exchanger, and the hot gas from the ammonia reaction goes directly into the plates and flows into the middle and out into the hot gas port, the red one. And then in the other side of the plate, you have the cold gas coming in. You can kind of see it in the right side how it works. So this cold gas is coming from the outside as well, from the ports, and also going, in this case anyway, towards the middle into the center port there where it's collected and sent up to the first bed. So here you can kind of see in this diagram a little bit better how it works. So the gas comes in from the top as it did before, right? Remember, we have to work with the existing nozzles as well. So the gas comes in from the top as before and goes down, still cold, into the first ports of the plate heat exchanger, and from there it flows into the middle through all the plates in parallel, and it gets heated up by the gas that's coming on the other side of the plate from the first bed. And from there, the cold gas goes back up to the top of the converter, and it is sent over to the catalyst bed, passes through the catalyst bed just as normal, and from there it goes directly into the plates again, where it's collected and sent down into the second bed just as it would now. So what does this mean? Why is this an advantage? Well, actually, as it turns out, the plate heat exchanger needs a lot less space within the vessel, right? So with this space, I think it's obvious what we would like to do with it. We would like to put as much catalyst as possible to help the conversion. And in fact, there are a few things we can change as a result. So most of the cartridges, they have also coming from the first bed, the gas is first collected in a central tube, as you can see, I think, in this animation here. It's actually this tube that's going up. I don't have a pointer, but this center tube can actually be eliminated. And when that tube is eliminated, you can see that it allows us, as you can see in the picture below, it allows us to have a wider catalyst bed. So this is a significant amount of additional catalyst that we can put inside the bed, which is of course good for the conversion. And down below you can see then what happens. Instead of collecting the gas and sending it upwards first to be sent through the shell and tube heat exchanger, the gas is sent directly into the plate heat exchanger where it's cooled by the gas that's on the other side of the plates. So here's an example of one study we did. This is not an Egyptian plant, but it's a 3-bed converter nonetheless, just to show you an example of what kind of results we can expect. So this converter was a 3-bed converter, but it also had 3 heat exchangers of shell and tube variety. So exchanging those heat exchangers and using plate heat exchangers instead, you can see in this table that we reduced the pressure drop by about almost 1 bar, 0.9 bar, even though we had 130% flow of gas going to the reactor. And this translated into an increase in the ammonia production of 124%. So as I said before, alternatively, if you would like to keep the production of ammonia the same, then you would see in this table instead, you would see a drastic reduction in the pressure drop. So instead of having 4.4 here, maybe you would have something like 3 or something like this. So this would be a direct way to save money, because then you save pressure drop over the loop. And as a result, then you save steam for the syngas compressor turbine, and indirectly you're saving then natural gas, because then your package boiler has to produce less steam. So this translates into direct cash savings. So I pretty much said most of the points already. Using this kind of a new technology, you can, with the same vessel, the existing vessel, with a new cartridge, you can produce much more ammonia, up to 20%. These kinds of volumes normally, when you want to produce this much more ammonia, typically you would have, in the past, you would have needed an additional vessel to install it in series with the existing converter. But this is a way to do it where you can do this all in one vessel, so you save on the piping. You would normally also need an additional waste heat boiler. So if you have 2 converters, you need 2 waste heat boilers or some way to cool the gas down again. So this all happens in one vessel, so it actually saves you on all those pieces of equipment. As I said, lower pressure drop, higher conversion rate, and the bottom line is this leads to either more ammonia production, which is more money, or energy savings, which most people are looking at these days, or let's say a combination of both. That's all I have for now. So I'm Happy to receive your questions. Yeah. Thank you.
Thank you, Fred, for a very interesting technical presentation about retrofitting. We have used 30 minutes, but I'm confident that most of the nitrogen ammonia producer have questions for Fred, so I'll allow for 2 or 3 questions at this stage. We have a question at the front. Manan?
Thank you for a very informative presentation. My name is Abdul Najjar from Bahrain, GBIC Bahrain. The question is regarding the retrofit of the secondary reformer and lowering the methane slip to very good value. Did you consider this project as energy enhancement on production increase?
I think probably it was a combination of both. I think it's a combination of both. So typically, with these kind of measures, you don't see purely energy efficiency benefit or increase of capacity benefit. Typically, you see a mixture of both, and that was in this case as well.
And the outage was within the available window for turnaround or whatever for this organization.
So the ring burner of this particular plant was exchanged already, I think, 5 times in the past. So this ring burner can be exchanged just like any other ring burner. So it only takes I think 1 week or something like this. So it's well within let's say normal turnaround time frame. Yeah. So it would be exchanged just like any other ring burner. The only difference is that the orientation of all of these nozzles and how everything works together is much more, let's say, optimized, right? So everything has to be manufactured in just the right way, but the actual installation of the ring burner is just like any other ring burner. Yeah.
Thank you.
Thank you, sir. I think we have a question from Dr. Awad, please.
Thank you very much.
Yes.
Thank you very much for this informative presentation. Coming back to the same question for the secondary reformer, are you just to change the orientation of the nozzles or also increase the number of nozzles?
I think both, yes.
Both.
So we optimized the number of nozzles and also the orientation and the way that I think you saw in the picture they're a little bit angled, right?
Yeah.
So this angle is actually very crucial, as it turns out. It has to be just right to create this this swirling effect that's so important for the mixing. Yeah.
Because we experienced catastrophic damage due to those nozzles, especially when the fire is straight heading to the refractory, and that end up with losing the thickness of the shell even.
Right.
And
right.
we just managed by increasing the number of nozzles and replacing the top dome of the secondary reformer. But this addition of the orientation, I'm sure it will be
Yes,
more
yes.
practical. Thank
Yes.
you very much.
Mm.
Thank you, sir. We have a question on the second row.
First, thank you for your excellent presentation. My question is about the cost of production of 1 cubic meter, for example, of ammonia in the old method compared with the new method. Can you give us some figures regarding this issue?
Unfortunately, I don't have those figures because the cost of natural gas plays an important role, and I don't know what they pay for the natural gas. But there was for sure an improvement. I think I remember that this new design had a payback time of only just a few months.
Yes, but it is feasible, economically
Yeah.
feasible.
Yes, yes, yeah.
Okay, thank you.
Thank you. We'll take 2 more questions. Ali? Start.
Hello, thank you. I'm Ali Fakhro from GPIC Bahrain. Thank you for your informative presentation. My question is about the secondary reformer. So, did you consider changing the gas distributor as well in your model design? And another question is what was it I was going to ask? Yeah, that's it. Yeah, did you face any challenges while fixing like actual fixing of the ring nozzle?
Yes, yeah.
on
Well,
site?
the challenges faced in installation, there were some because as it turns out, the old pipe, the air pipe coming into the secondary reformer, it wasn't according to the drawings anymore. It wasn't round, but it was like oval, right? So the new ring burner was designed according to the drawings, what we thought it would be like, but unfortunately it was a little bit different. But this turned out to not be a problem, but it took a little bit longer than anticipated, but still we did this within 1 week, and we had our people there assisting our customer, and he has a great team as well, so it turned out to not be too much of a problem. I forgot the first question, sorry.
The gas distributor.
Oh yeah,
the design.
the distributor, this was also the plan at first, to look at the distributor, but the first CFD models, they showed that the real problem was with the ring burner, and it wasn't necessary to change the distributor. But it was originally our plan to look at that as well for exchange, but it just, we figured that it was just not necessary.
Engineer Khalid, two more questions. I'll take two more questions.
Thank you, Mr. Kessler. Very nice presentation. My question regarding the ammonia converter. It's very promising and marvelous retrofitting for the new basket. My question regarding the internal heat exchanger, split heat exchanger mainly, regarding the gaskets which holding the plate itself. I know this suffering before from many conferences we held from the gaskets and some catastrophic failures from the catalyst when the gasket is failed. What about the gaskets of this exchange? Because it's welded gasket.
Yes, thank you, Khalid. So in this case, everything will be completely welded. So there will be no normal gaskets like you would see in a water cooler or something like this. This will all be welded together, so there will be no leakages.
Thank you.
Yes.
Last question, please.
Thank you for this presentation. I want to ask one question for the two cases. First one, second reformer modification means more hydrogen produced. And you must remember what is the nitrogen available for ratio after synthesis. Second point, what is the efficiency of heat recovery after the converter? Because you increase the production by 28%, you must be sure that the heat recovery units can give this type of modification.
Right, that's correct. So the additional nitrogen that we would need for the ammonia production because of the improvements here, this is true, but in our experience, the process air compressor is more than capable of delivering this extra amount of air, so it's no problem. And the important thing to note when you make a huge jump in capacity like this, let's say 24%, this is for sure not the only change you would have to do in the ammonia plant, right? Because most likely the front end of the plant would need to be modified as well, because I don't know any ammonia plant that could just produce 20% more syngas just by pushing a button or something like this. So this would be one measure as part of a revamp, right? One of many measures, but this would be a lower cost way to do a revamp of the synthesis section. Since, as I said in my presentation, normally to get these kinds of additional capacities of 20%, 30%, you would need an additional reactor with a new pressure vessel, an additional waste heat boiler, plus all the piping. So this is a much cheaper way to get the ammonia production, but for sure you would have to do some more work in other parts of the plant. Yeah.
Well, thank you, Fred, for this very interesting presentation and Q&A session. Please join me in thanking Greg by giving him a big hand.